Hello everyone, and welcome back to another video. And sorry, I haven't recorded a video in quite a while, mostly because my ambient temperature has actually been hitting around 40 degrees, and my room is on the uppermost floor, facing the south. So I spent most of last week being miserable and not feeling like doing anything. But, well, one thing I can do is just make PCB overviews because, well, I don't need to run any hardware for that, which I also can do because ambient temperatures are so high, my water cooling is less effective than air cooling is when normal temperatures. Alright, but let's get into this. So, today we're going to take a look at the HD7970 and also HD7950 reference PCB. And with reference PCB, I mean the PCB you're gonna get if you buy a blower card. And there's some other custom cards that have this PCB as well. But the thing for the 7950 and 7970, especially for the 7950, there are like two reference PCBs. The other one, Buildzoid already made a PCB breakdown for, but this one he didn't, which is basically why I'm making this video for, because, well, if Buildzoid already made a video, frankly his content is better than mine, so I just don't bother. But as far as I know, he hasn't made a PCB, well, I call mine overviews because I don't do efficiency. Yeah, he hasn't made one for this, so basically we're gonna take a look at this today. Yeah, so this is the PCB you're gonna get when you buy a blower, like a reference card with the AMD blower cooler on it. 7970 and also 7950. This specific card is actually a custom card. However, I think most of the custom cards use the other reference PCB, which is using, well, it has an additional VDDC high phase, and it has different Mosfets in its vCore and like just generally different Mosfets. Like this one is using IR direct FETs, the other one is using normal discrete Mosfets. But these are also discrete Mosfets, but not, these are IR direct FETs. But yeah, speaking of IR direct FETs, let's get into, yeah, the VRM of this PCB. So, most important VRM is our vCore VRM, and that is this entire block here. So on this card, it's a 7-phase. Never mind, it's a 6-phase. The other reference PCB has a 7-phase. Yeah, so this is dropping down 1 phase, and actually if you buy a blower card, because this came with a custom heatsink but still using the same PCB. But I also have another one of these PCBs that did actually came with a blower card, a blower heatsink, and the blower heatsink cards do not have this phase. It's just empty. So the blower cards run a 5-phase, and I think if you're dropping down to a 7950 from a 7970, you're actually losing another vCore phase and you're getting a 4-phase. So yeah, so the 7970s come with a 5-phase and 7950s, as far as I know, with a 4-phase. But then the custom cards that still use this PCB come with the full 6-phase, like this one. Yeah, and all the Mosfets for all the VRMs on this card are the same. So I'm gonna get into that a bit later. First, I'm gonna give you a general overview of all the VRMs. Up here we have our single memory phase. This is also a difference to the other reference PCB, because the other one has the memory phase all the way at the bottom, whereas this one has it at the top, which is, I think, the better place to put it, because, well, this way it's kinda like the same distance to the farthest memory chip, whereas if you have it down here, it's a very short distance here, but a very long distance here. So I think having the memory phase up there is actually the better choice. Yeah. And then we have another single VDDCI phase, so memory controller power, over here. And yeah, so our VRM controller for the first 2 rails is over here. That is a CHL A228G running in 6+1 phase mode. So this is an 8-phase controller, and it supports dual output, so it's controlling both our vCore and vMem. And yeah, so we're using it in 6+1 phase, so 1 phase goes unpopulated. And yeah, that's basically it. Like if you want to know a couple more things about the controller, so it supports switching frequencies from 200 kilohertz all the way up to 1.2 megahertz, which that's very high. I think this VRM comes with 300 or 500 kilohertz. I think it comes with 500 and I just set it to 300 because this VRM actually gets a bit hot if you really push the card, because this is just a thing, like, yeah, like, because the other 7970 PCB you can get has 7 phases, this has 6, and this also only has 1 low-side MOSFET per phase, whereas the other PCB has 2. Admittedly, these are stronger MOSFETs, but still just 1. Yeah. So, that's our controller. It is volt moddable by just, so this controller is a bit funky because, yeah. So you can't really feedback mod this one because it doesn't really have a feedback pin. It just has a VSEN or voltage sense pin that, judging by the typical application diagram, just goes directly to the output of your VRM with nothing in between. So this pin is going to have the resistance of your GPU core because that's the only thing between that pin and ground. You can still volt mod it, like I have done it on this card. You can see it here on the picture. The blue wire is a volt mod, and it's going to I think a capacitor resistor that is connected to the VSense pin. And yeah, I just used a 100 ohm potentiometer, I think, and then you can see the other ones just going here to ground on that screw hole. And the volt mod does work. It's just very funky, and apparently it can cause issues where, like, your voltage change, like, apparently there's an issue with it where your voltage just keeps climbing and climbing and climbing, and it gets even higher, just because you're messing with dye sense here, or more or less. Like, usually you have a voltage divider. This one doesn't have one, so weird things can happen. But yeah, on this card it's been working fine so far. And yeah, but I would prefer only having to use the I2c lines on this controller, which I have actually done. These 3 wires are for the I2c interface. So the white wire is again ground, and then the yellow and red wire, these go to some, I think, capacitors that are connected to the one of the pins. It should be SMB_DIO and SMB_CLK. That should be the I2C pins. They usually have like SDA and SDL labels. On this one they are labeled the other thing. Sadly, this one doesn't have like a pre-made I2C like connection port where you can just put in a connector and then you have it, which is only on the other PCB. On this one you actually just have to solder to some things on the PCB. Like, it works, it's just I kind of ran out of headers, so I'm just using alligator clamps to connect to this, which is a very, very, like, if something shorts there, you're probably gonna have a bad day. Yeah, but you can use the Elma EVC with this card. Sadly, this one also has a voltage lock at 1.38 volts. You can't go higher than that, which is why there's a volt mod, because I want to go higher than 1.38 volts. Yeah, but you can also, like, basically what I've been doing is I've been using the volt mod as like a static offset to my voltage, and then using fine-tune with the EVC. It's just the voltage the EVC reports is probably gonna be wrong. So you're gonna have to, like, measure your voltage physically behind the core. Yeah, so moving on to the, yeah, I mean, okay, VDDCI VRM is just one phase. The controller for it is on the back. I do not know what controller that is. Like, yeah, I didn't look this one up because, well, there's some places where you want to overvolt VDDCI, but I couldn't really be bothered to look up that controller. Yeah, so I don't really have any info on it. And yeah, so let's get into the MOSFETs for this. So all the VRMs, so all the major 3 VRMs, there's also smaller ones like 1.8 volts and packs and 5 volts, like, yeah. but the core, memory, and VDDCI VRM all use the same MOSFETs, which, as I've already said, are IR direct FETs. So our low side MOSFET is a, and this gets funky. So our low side MOSFET is an Infineon BSB 013NE2LXI. Now that's a funky name. So even though these are using the like typical IR direct FET package, these are not actually International Rectifier branded. They're just using the same package. And the thing that's written on, so the MOSFET physically on it written has 02E2. And if you try to Google that, you're not gonna find anything. So this is the point where I'm gonna give a shout out to Buildzoid, because I posted in his Discord, be like, does anyone have an idea what MOSFET this is? And he just, basically he went to the Infineon website and just started looking up random datasheets of MOSFETs until he found two that in the datasheet said, oh yeah, they are marked exactly this. So that's how I found the datasheets for these. So yeah, thanks to Buildzoid for spending some time trying to find out what MOSFETs these are, so I can tell you specifics. Yeah. So, continuous drain current for the low side MOSFETs at T case 100 degrees, so that's the case of the MOSFET is at 100 degrees. It has 103 amps of continuous drain current, so that's at 100 degrees case. And they sadly don't give one for ambient 100 degrees, but they give one for 25 degrees, and it has 36 amps of continuous drain current at 25 degrees ambient, that is case. And then at 25 case ambient, it's 163 amps. So basically this follows the typical IR direct FET curve. These MOSFETs have a lot of continuous drain current when they're cold. They drop off quite a lot when they get hot. However, I think, well, like the case of the MOSFET was hovering at probably around 60 to 70 degrees while I was pushing the card. So that's still quite some way away from those 100 degrees. So we are somewhere between the 163 and 103. I have no idea what the curve actually looks like, but I would imagine like 120 amps would be possible. And that's quite a lot. Like that's pretty far from maxing out this MOSFET, because we do have 6 of them. And we're just powering a Tahiti core, which is not that power hungry. Like, it's not a Hawaii core, it's just a Tahiti. Yeah. Then, does this datasheet actually mention RDS on? I have not looked at that. Yes, it does mention RDS on, and it's 1.3 milliohms. That's actually pretty good. Like 1.3 milliohms, that's nice and low. Like this is, yeah, like basically this doesn't produce a lot. Like this is gonna be pretty efficient, but the VRM still was getting kind of up because the heatsink on it is not that great, and it is still just a 6-phase. However, because these are IR direct FETs and you can see they have like this metal package, these are a lot better at conducting heat. So the delta between outside, like their case temperature, and the actual internals of the MOSFET is much, much lower than normal MOSFETs, which might feel like the VRM is running hotter, when in reality it's just better at getting the heat out of there. So the temperature component of this VRM is probably well within control. It just might feel a bit hotter. So getting to the high side MOSFET, that has an equally interesting name, which is the BSF 030NE2LQ. And the marking on this one is 03E2. So that's the actual marking of the MOSFET. But yeah, so that's the actual part number here that you want to look up if you want to see the datasheet. RDS on this is 3 milliohms, which is fine. It's a high side MOSFET. Like they don't have to handle a lot of current, even though this one still has quite a lot of current capability. So this one has 47 amps at 100 degrees case temperature, and it has 24 amps at 25 degrees ambient temperature. Oh, I think it might be a bit too late, but like the ambient temperature is like the MOSFET on a PCB with no cooling whatsoever in given amount of ambient temperature. It doesn't have a heatsink on it, which is why the 25 degrees ambient is usually the lowest current rating. Yeah, and like you can, it's not that like, okay, the 100 degrees number is quite a bit off, but like the 25 degrees ambient temperature is kind of, yeah, like this can still handle a bunch of current. And now I need to find, I really should have looked at those data sheets more closely before making this video. Okay, so rise time 3.4 nanoseconds, fall time 2.6 nanoseconds, turn off delay time 18 nanoseconds, turn on delay time 2.8 nanoseconds. I don't exactly have good numbers to compare against in my head, but from what I remember from different high-side MOSFETs, that's pretty fast. Except that turn-off delay time, I'm not so sure about that, but the rise time and fall time, and I think to also turn on delay time, those sound pretty fast. Like under 5 nanoseconds for all of those. So that sounds pretty good. Like, yeah, that sounds pretty good. And yeah, so every VRM in this on this card, or like the 3 main ones, use these MOSFETs. All use one high side, one low side per phase, which, yeah, that's fine. Like, it's a Tahiti core. I don't really know what to expect in terms of power consumption under liquid nitrogen, but with water cooling, I think the farthest I've pushed these is around 300 watts at like 1.35 to 1.4 volts behind the core. So that shouldn't be too bad for the VRM. Like, the VRM should handle this just fine. Even, well, I'm not so sure about the 4-phase. If you get like a 7950 and it only has 4 phases, that might get a bit too close for comfort, but I think even the 5-phase variant you get with a blower... Well, if you use the blower heatsink, you're gonna run into a thermal limit sooner than running into like a VRM limit, but I think even the 5-phase version of this PCB should be fine for like pushing it on water. For liquid nitrogen, it might be a different thing. I've never run anything sub-ambient. I do have an LN2 port, but I've never used it. That I do want to use it as soon as I can. It's just that, well, weather is non-optimal right now, and the ambient temperature is still kind of high, so I'm gonna have a lot of condensation, and I don't feel like dealing with that. So, yeah. So we're done talking about phase counts, we're done talking about controllers, we're done talking about MOSFETs. So let's go to capacitors. So I kinda like the output filter on this. It's not super strong. I think actually the other reference PCB has a better output filter, because this one just has its polymer caps in one row, whereas the other reference PCB has kind of like them in this zigzag pattern, allowing it to effectively have more capacitors in pretty much the same area. So this is gonna fall behind total, like in total capacitance, behind the other VRM. However, those are all still 820 microfarad capacitors, and you still do kinda get a lot of them. Yeah, that's 8. But you also get all of these multi-layer ceramics here. That's one thing I really like. So, I don't think they do really a lot, because they are at the VRM output, not behind the core. And usually multi-layer ceramics don't really do a lot when they're far away from what they're powering. But it does help, like, a little bit. And I think it's nice of them to put this in here. I think it would have been more effective if instead of multi-layer ceramics they would have used, like, SMD polymers. But I think AMD just didn't really like using these a lot, because I don't think... I can't think of a reference PCB from that era that uses these. Or really any... Well, the MSI Lightning used them. And I think that's about it. So, yeah. But that's still it's miles better than what you get on NVIDIA reference cards. So yeah, that's pretty nice. Also the input filter on this, that's like, oops, no, I didn't want to do that. Oh, come on. Sometimes OneNote is just being stupid. Yeah, like, you get input filtering here, input filtering here, input filtering here, and then you get this row of multi-layer ceramics. This thing has a ton of input filtering, which probably would make 60900 XT owners very, very happy, because, yeah, okay, these are 270, this is 150, 150, 150, 150, and this is probably gonna be another 150. So, but like, yeah, so it's 6900 XT has like 5 150 ones. This one also has 5, but it has these two, and then this array of multi-layer ceramics, which I think is more substantial than what the 6900 XT has. Also, there's 2 more input filtering capacitors here. So, yeah, the input filter on this is probably pretty decent. Though I have to say, a bunch of these multi-layer ceramics are missing if you get the blower card variant. Like, it's not just missing that one phase, it's also missing some of these multi-layer ceramics. But it does have all the CAN-type capacitors. So, yeah. The pads are still there though, so you can just like mod them yourself. And yeah. Oh no, never mind. There are multi-layer, there are SMD polymers over here. Yeah. VDDCI has these as output filter. Probably because of heatsink clearance. But yeah, so like if we had a bunch of these instead of all the multi-layer ceramics at the VRM output, I think it would have been a bit more effective, just because multi-layer ceramics so far away from the core probably don't do much, but I'm nowhere near good enough in electrical engineering to really know what would happen. And yeah, so on the back we don't really have a whole lot, like just some multi-layer ceramics for like behind the core and behind the memory. I do have this modded. The card doesn't come like that, of course. And yeah, so we have some drivers here for our phases, because the CH8228G does not include drivers. This controller I think does, because I can't see drivers anywhere here. So yeah, like these smaller controllers usually include drivers. The big ones that have like a bunch of phases usually don't, from what I see. And yeah, I mean, there's nothing really too interesting on the back. Just like, here's the PAX rail. This should be the BIOS chip. Here's the other BIOS chip, because this has dual BIOS, like the BIOS switch is over here. There we have the BIOS switch. And yeah, I think that should be mostly it. So it's another AMD reference PCB, and usually AMD reference PCBs are pretty decent, if not really good. Like, I think for the 5700 XT, quite literally the best PCB you could get was just the reference one, because most of the other custom PCBs just cheaped out on stuff. This is by no means the most powerful one. I think the most powerful VRM you can get on a 7970 would be the Matrix, because that has 16 phases. Well, the Lightning is probably not that far, because it also has 14. Yeah, I actually don't know. The Lightning might be more powerful, because the Lightning is also using IR direct FETs, whereas the Matrix is using dual N FETs. Not sure, but like, yeah, this is nowhere near the top in terms of current handling capability. However, we're still talking about a Tahiti core. And yeah, like from what I've said, like I wasn't really able to go anywhere over 300 watts on these. So yeah, they like, well, 300 watts is still kind of a lot, but considering that this VRM is using some really, really nice Mosfets, and the output filter, okay, the output filter doesn't really do anything for current handling capability, but, well, bigger GPUs that consume more power have nastier transients, so I need a better output filter. But yeah, I like this PCB, and that's one of the contributing factors as to why this is actually currently my favorite 7970. mostly because this one just has a really good core. This one runs 1400 megahertz. The memory on it is pretty bad. It's MFR. Like, this is an OG 7970, and the OG ones come with MFR, so that's kind of a trade-off. Like, the OG ones have usually better cores, but have worse memory, so it's kind of a trade-off. But yeah, this one runs 1400 megahertz on water cooling. Which is why, yeah, I've so extensively modded this, and I'm not done. I'm gonna put more multi-layer ceramics behind the memory. Like you can see, I put one here and then gave up. But yeah, I'm gonna put more multi-layer ceramics behind the memory, probably behind the core. Probably put some more polymers on there as well, because, yeah, like, that's a nice thing you can't do with NVIDIA cards. If you have like a reference 480 or 580 or a reference 780 or 780 Ti. Also, basically any NVIDIA card that's reference PCB and not the 1080 Ti or newer, you can't really push them really, because the VRM is gonna be maxed out before the core is. That isn't really a thing on AMD. Like, these VRMs should be plenty powerful, so they're perfectly usable for if you just get a good core. Well, it's perfectly valid to run a reference card over like a Lightning or Matrix, because if you just get a really good core, this VRM is powerful enough to push the card, and like, there's also ample room for modding. Like, as you can see, I put all of these capacitors here, and I'm not done yet. So, yeah. Like, I really like this PCB. And yeah, like, it's another thing why I think 7970s and 7950s, and then of course also 280Xs and 280s, because those are quite literally the same card. They are very fun. Like, they don't consume so much power that you really need water cooling to get anywhere near good clocks. They have decent PCBs. They're not too expensive. Like, sometimes you can get them cheap. And they have great scaling, and you can also mod memory timings on them, which you can't do on NVIDIA. Like, they are just... You can just do a lot of things with them, and I'm really, really happy that even if you have a reference card, the PCB is probably not gonna hold you back. Well, modding on it is still gonna have a bigger gain than like a custom card, but this is not gonna hold you back in the way of, oh, the VRM is gonna explode if I push it, which is a thing on NVIDIA. So, yeah, I like this. It's not as powerful as the other variant you can get, I think. Like, this one has better Mosfets, but the other variant just has a more substantial output filter. It has more phases, it has more Mosfets. It also makes it much easier to hook up an EVC to it. But I still like this PCB. It's, yeah, I mean, it's even though like there wasn't a pre-made A2c port or anything, I still was able to mod this just fine. And yeah, so I like this. And the video is getting close to 30 minutes now, so I think we should end it here. I think I've said everything I wanted to say about the this PCB here. So yeah, thank you for watching, hope you enjoyed, and until next time, goodbye.